Okay, can you see that okay? I assume you can. Okay, so look, it's really wonderful to be part of the Digital Futures event again this year. I've very much enjoyed being involved in this over the years, as Philip mentioned. So today, what I want to talk about is 4 aspects of the work that we've been doing over the years. So part of this has got to do with generative design and algorithmic processes. One aspect is about the generation of complex and intricate forms. A third is around robotics and automation and additive manufacturing. And I guess the fourth and perhaps the most important part of this is around tectonics and the way these other 3 elements come together to create innovative and intricate tectonics. So this work really dates back to the first practice I established, Kokuja. Now this was a collaboration with Jonathan Popolosek, Robert Stewart Smith and myself, and really became a platform for Rob and I to develop a whole series of algorithmic explorations. And in many ways, this was an attempt to try and understand what perhaps the limits of generative design or algorithmic design might be. And it was very much a research practice, not established to try and build projects per se, but instead to try and experiment and to test what's possible, I guess, in a slightly whimsical way. That practice sort of drew to an end about 9 years ago. And around that time, I moved back to RMIT and began establishing a lab. And this has evolved over the last 8 or 9 years and has recently been rebranded the RMIT Architecture Tectonic Formation Lab. And this is really trying to reflect our interest in innovative tectonics and the way they come through the formation of algorithmic systems and robotic fabrication. So from an algorithmic side, the lab is dealing primarily with my interest in multi-agent algorithms and also the interaction between this and AI, machine learning, and in particular reinforcement learning, and the way these 2 algorithms start to relate to each other in terms of one being from the bottom up and then one dealing from effectively the top down, dealing with surface conditions, and the way the 2 of those algorithms start to interact. The other aspect of the research is around robotics. Most of our work now is around additive manufacturing through a series of different materials. And as I said, so this comes together in order to make innovations within tectonics and trying to experiment and speculate on what the potential tectonics might be when you start to bring together algorithmic self-organizing logics and robotic fabrication. So this is the team. There's 8 full-time researchers in the lab, and these are our facilities at the Design Hub at RMIT University. The third part to my practice is Studio Roland Snooks. So this is an architecture practice which is trying to take the innovations that were originally developed through Kokuja and are now being further evolved through the Tectonic Formation Lab at RMIT. It's trying to take those and then realize them through live projects, through architecture projects within the world. And so this is where a lot of the innovations then have to rub up against problems of building codes and fire codes and how we transfer or translate innovations that have happened in the lab. How do we get those into industry? How do we find industry partners who are able to then engage with this and start to build some of these projects? So the first part of the presentation today is around process, and in particular around a generative design process that I describe as behavioral formation. So behavioral formation is an algorithmic logic which draws from the logic of swarm intelligence and the operation of multi-agent algorithms. So this is an approach where the individual designer or architect's intention is encoded within a series of semi-autonomous computational agents. And it's through the interaction of these agents that some type of emergent collective behavior arises and a sort of self-organized design intention comes out of these systems. So these are the type of systems that we see within systems of swarm intelligence and collective behavior. So whenever you have a set of entities and through the interaction of those entities, some type of higher level collective behavior emerges. So in this type of work, it's never a single behavior that drives the logic of the system. or neither is it a hierarchy of behaviors. But what happens is it's a series of behaviors which all interact and negotiate between each other. So the interesting thing for an architect here is that we can then describe a whole series of architectural decisions or behaviors or intentions and look at the way we give those various weightings and allow them to interact in order to negotiate a sort of cohesive whole. These are the types of behaviors that we write. They're all vector-based multi-agent behaviors. And we're interested in what substrate they are then embedded into. So often I think when people think of multi-agent systems, they're thinking of the type of swarm systems that we see in flocks of birds, schools of fish, social insects, and where we have the agent is a point. We're much more interested in higher level instantiations of agency within geometry. So we're interested in the way agency can be instantiated into a strand or instantiated as a vertex into a network or a mesh. And perhaps the most sophisticated level of this is something we describe as an agent body. And an agent body really is a collection of agent-based strands where each limb has a series of points in which agency is encoded into them. So in this way, the agent body can navigate space, but it can also begin to make connections to its neighbors through these limbs. And the second half of the presentation will focus very heavily on this algorithm. This has been a sort of driving force behind the work we've done, particularly over the last 10 years. So here's an example of a collection of agent bodies and a short video where you can begin to see very subtly these limbs start to move and connect to each other. And what they're doing is creating continuous lines of structure and ornamental networks. So this type of logic makes a type of geometry which is neither surface, volume, or lattice, but creates something that's in between. And we sort of think about this as being a thick fibrous mass that it makes. And we're really interested in the spatial and formal implications and possibilities of this type of work. Now, of course, this also represents a whole series of problems in terms of how do you go about building and fabricating these very non-standard geometries. Of course, when you're building at a small scale, the solution is fairly obvious. It's through small scale 3D printing. So this is an object which is not very large. It's about 600 millimeters across. It's directly printed using an SLM, a selective laser melting technique, and it's printed in aluminium. So you can see it's here. It's printed with a fair bit of support material, which is then removed. And so this type of technique allows us to make things which are, I guess, very fine grained and have a high level of intricacy. This is produced from an agent model with over 1 million agents. And each member of this lattice is only about 0.4 of a millimeter in diameter. So it's a very fine network of members. In this project, we are trying to create a series of different conditions. So the edge conditions begin to sort of fray and become sort of fine filigree, whereas underneath the wings, we have these much more sort of turbulent, thick masses to the project. So this was a small object, which was really a retroactive form study that evolved from a bridge project that we were working on. It was exhibited at the Pompidou Center as part of the Code Le Monde exhibition about 2 or 3 years ago. And this was an exhibition which was trying to trace the history of algorithmic work through a series of design and artistic disciplines. That was actually a secondary project to this earlier project. This is a similar type of printing technique, but using titanium. This is a project for the RMIT Ceremonial Mace. So this is a ceremonial object, which is, I guess, a ceremonial weapon in a way. And it's intended to be a symbol of the university. So it's an attempt to try and symbolize the innovation within the university in terms of fabrication and additive manufacturing and advanced manufacturing, as well as generative design and computational design. So it draws on the history of ceremonial mace, which are highly intricate objects. And we're trying to reinterpret that intricacy through, of course, new computational approaches. So in a similar way to the previous project, the 9 Elms project, this has a thick fibrous mass. But as you move down the shaft to where the object is held, there becomes a shift from something which is generated through a bottom-up, highly generative, self-organizing logic, which I guess in many ways is volatile and wild, down into something which is much more controlled and directly modeled or drawn. So this area where you hold the mace has been directly modeled. this difference and translation or transition and relationship between things which are directly modeled and things which are self-organizing and evolving has become increasingly a key part of our work. And I'm going to try and explain how that's operated through a series of projects over the last decade or so. So in this project, it was printed in 4 parts. You can see this is the jointing system. It was then joined together with laser welding under a microscope, sort of a jewelry technique, I guess, to join these parts. It's not a very large object. It's about 1.2 meters in length. But you can see the cross-section through the handle of the project, where the agent bodies begin to compress towards the surface and make this sort of thicker outer crust. And then the internal structure is something which is, I guess it's a highly optimal structure in that it's a very intricate lattice that makes a very stiff and strong structural cross-section. But at the same time, of course, it's part of a larger expressive system. And this is something we're always trying to do. We're always trying to look at what is the relationship between things which are highly expressive and things which are structurally optimal, and what is the balance between those. And I guess part of our logic of negotiation within architecture is not to try and create something which is one or the other. We're not seeking to try and make the most structurally performative project we can. Neither are we trying to make something which is overtly expressive. We're looking at the way these two things negotiate and come into some sort of synthetic relationship between the two. Of all the projects we've done, this is perhaps the most purely algorithmic of the projects. But at the same time, we're quite critical of this way of working. We're quite critical of a lot of what happens within algorithmic design and generative design, because we see so much of it as being a shift from the original ambitions of generative design, which was very much about speculation and experimentation, into something that has become an active selection. And what I mean by that is that increasingly we understand the indexical relationship between an algorithm or procedure and the type of form that it creates. And if that has a very strong indexical link that we understand, then every time we use an algorithm in order to design, what we're actually doing is we're pre-selecting an a priori formal characteristic or formal quality that we want for the project. So this no longer is a sort of act of experimentation or speculation. Instead, it's an act of selection. So algorithmic design becomes an act of selection, not of speculation. And so what we've tried to do is try to work out ways in which we can bring algorithmic self-organizing logic into some sort of interaction with other mechanisms, whether they're sort of top-down operations, painted operations, or material behavior, and then look at trying to create hybrids which make qualities which are no longer indexical to their tool. And so this is one of the early examples of that. This is a project which was testing an approach we describe as painterly formation. And so painterly formation is where we have a self-organizing algorithm which is constantly interacting with manual human gestural operations, where we're literally sort of painting the geometry and going back and forth between something which is self-organizing and then something which is being directly painted or brushed. And in doing so, we're trying to create hybrid characteristics which, as I said, can't be indexed back to one or the other operations. So I guess this brings me to the next part of the presentation, which is around form and our interest in form and consequences of that. So this is a series of projects initially to kick off this discussion, which are around these painterly operations, where we're trying to make highly intricate objects, but not objects which can be indexed back to their generative or painterly operations. This is something that we also work on with students. This slide is student work from RMIT University, where we're encouraging the students to try and work through these processes in order to generate or to create their own aesthetic sensibility. And so aesthetics and form is something that we spend a lot of time talking with students about. I think often these things are seen as slightly frivolous within architecture often, but that's not the way we think about these things at all. We think about form and articulation as something which carries everything else. It's something which then embeds structure and program and the performance of something within its geometry. Another approach to undermining the purity of algorithms is through material behavior. So this is quite a sort of a caricature of a project in many ways. This is an attempt to try and bring material behavior or material agency and computational agency into a real-time feedback, into a project in which the robots are scanning what they're producing while they're extruding material, and they're constantly responding to that material. So the idea is that there's no predefined design for this project. There's simply a series of behaviors that are written directly to the robots. And so the robot's treated like an agent. And that agent's making a series of decisions about extruding material. As it's extruding this material, we're trying to use the most volatile material we can. So it's this sort of slightly grotesque expanding foam. And while this material is expanding, the robot's responding to what it does. It's scanning in real time and then making a series of new agent-based behaviors or decisions as to what it does next. And so the idea is that the forms we're trying to create from this are forms which are neither purely about the material behavior, nor are they about the agent-based behavior, but they become some sort of strange hybrid of the two. And we're interested in what different types of characteristics that then generates. So obviously this again is slightly sort of an absurd project, but what we're trying to do is demonstrate the point that these processes don't have to sit in some sort of sequential relationship, but they can actually be engaged in a very sort of deep real-time feedback approach. This interaction between the generative and I guess the top-down is something that I began working on with Tom Wiscombe in this project. This is now, I guess, 12 years ago. So this project for a pavilion for the Yosu Expo, this was really looking at how we start to blur the relationship between things that we model and things that we generate through algorithms, and how we begin to create, sort of shift from an early sort of Frankensteining of these two into something which then becomes synthetic. There's sort of, to create a condition in which it's very hard to understand the source of formation. So algorithmically, we're working on a multi-agent system which generates strands. These strands begin to bifurcate, and they create these types of networks. So I guess that's in its most pure state. But then, of course, we started to look at the way that related to forms that we're modeling. And this is an approach where we would model something, we would then put it into the algorithmic system, we'd then bring that out again, we'd remodel the results of that, put it back in, constantly go back and forth from these sort of slightly Frankenstein, almost collaged relationships, until it creates something where there's a synthetic relationship between the two. Another aspect of our work that's evident in this project is something I describe as polyscalar tectonics. And so this is an attempt to try and create something in which the same tectonic logic happens at a series of different scales. So you see the same formal conditions happening at a sort of spatial scale, as well as a scale of structure, right down to something which is ornamental. And so what we're trying to do is blur the relationship between a particular geometric type and the role that it plays within architecture. I'll talk more about that in a moment. Other formal concerns we've had in the work, and this is what I'm showing now is some of the older work, is about trying to create a synthetic relationship between surface, articulation, and structure. So in this project for the National Art Museum of China, a competition entry that Rob Stewart-Smith and I worked on together, what we're trying to do is to create a formal condition where the overall language of the form, as well as the language of the articulation and structure, appear to come from the same process, appear to be created from the same, I guess, emergent condition. There's also a blurry relationship between the forms we're interested in and articulations or ornamental conditions. And so this is one of our early projects we worked on with agent body algorithms. This is back in 2009, where we're interested in the way figures emerge from fields. But as you start to zoom into these, you see a whole series of different conditions emerging. So on the left, you see something which is sort of singular condition. On the right, we have periodic conditions. And as you zoom in further, you can see sort of near symmetries. None of these conditions are conditions which are programmed into the agent-based system. These are all conditions that emerge from the interaction of the agents. This interest in highly intricate geometries extend to projects such as this for the Kazakhstan Expo, sort of highly fibrous projects, as well as projects where we're looking at how we might build those through, for example, for this project, it becomes a structural shell. I'll pause on this project to try and also explain more about this relationship between architectural role and geometric type. We're interested very much in decoupling an architectural piece of geometry from the role that it plays. So for example, a column is dealing with the transfer of vertical load, and so there's indexical relationship between the role that it plays and the object that it is. In this type of project, there's a single piece of geometry, this concrete outer shell, which is working structurally. It also becomes ornamental. It becomes the skin of the building. Parts of it begin to inflate and become spatial. And so what happens is this is a single piece of geometry which is negotiating between a whole series of different architectural behaviors. And so I guess this is something where we begin to sort of shift the way we describe things from an architectural role to the way something behaves. So how does structure behave? How do spatial conditions behave? How can these be programmed into multi-agent systems where they become behaviors or rules that lead to the generation of these types of geometries? Over the years, our interest in form has shifted from highly expressive forms to actually more mute forms, where the expression comes from some type of tension between the muteness of the form and the intricacy of its articulation. So this can be seen in a project like this. This is a meeting pavilion that was developed for the design hub at RMIT University, in the building which I work in. And this is a fiber composite project. So it's created from fiberglass, where the skin is relatively thin. It's about 5 mil thick. But then this series of agent body articulation across it, then have a core material in it. They create a structural thickness to the surface. And so what ends up happening is this pattern is a negotiation between the structural necessity of the form, an expressive logic, as well as questions around relationship between pattern and form, and pattern and aperture, and the way parts of these become more translucent. That's it during fabrication. This logic between pattern and mute form is something we also explored in this project for Scentsy Lab. So it's a research lab that we were asked to design. This is a project through my practice studio, Roland Snooks. And it's a research space in which there are a series of objects or pavilions that contain very specific programs. So one of them is an immersive theater, another one's a sound recording space, another one's a photography studio. And between each of these objects sits an open plan office space, which is a series of sort of meeting spaces and hot desking, etc. With the objects, they're generated through a series of positive and negative volumes and intersection between these. And sometimes these intersections are virtual intersections, which create the patternation for the objects. And so as you move around the project, these three-dimensional forms begin to come into focus. So for example, in this particular view, you can begin to see how one three-dimensional form is carving out or inscribing a pattern across these two adjacent volumes. Sometimes those negative volumes become real Boolean objects. So for example, here you can see how an object is then being used as a negative volume that carves out of these two volumes. And this becomes most extreme in this part of the project, where it begins to carve out quite a sculptural space through this exhibition area, creating a series of plinths, and then also perhaps my favorite part of the project, this massive oversized capital, where the capital of the column is significantly larger than the column itself. Inside one of these pavilions is a sound recording studio, and what we're trying to do in this space is to try and create a space which has the appropriate faceting to create appropriate reverberation and reflection and refraction of sound, and then also a relationship between those large-scale facets and a small-scale articulation of it. And that articulation, in this case, is milled acoustic foam, which is being generated through, I guess, a two-way process of painterly operations as well as self-organizing operations. And this is something where we're using, I guess, a very known reaction diffusion algorithm Probably in this case, it's quite indexical, but the input becomes a constant redrawing of the pattern. So it's redrawing that reforms, it's redrawn. And so you begin to get a series of conditions which are perhaps more unique, as well as other conditions which blur out into more generic reaction diffusion qualities. So this is obviously performing a dual role. It's a highly ornate interior for this space, but of course, it's inherently performative. And so I guess this is what this might be a basis for a discussion towards the end of this presentation today is if this forum over this week is around performance-based design, I guess our work is always using performance criteria as a way of conditioning design rather than leading design. So again, this is not a pattern, which is something that is designed to optimize reverberation of sound, absorption of sound. At its core, it actually has something which is about ornament and expression. But of course, it's entirely conditioned by the logic of acoustics. So through the generation of this process, it ends up evolving into something which is then highly performative from an acoustic standpoint. The relationship between mute objects and their highly articulated interiors, I guess, began in this project back in 2010. This is a memorial and museum for Baba Yar, so it's a Holocaust memorial. And it has a stone exterior to the museum, which is sort of this heavy mute object that cantilevers at one end as though it wants to fly. But as you move into the interior of the memorial space, this becomes a highly articulated, highly intricate bronze cast memorial interior. And so we're interested in the juxtaposition between those two different conditions. That, of course, is generated by a multi-agent agent body algorithm. This is the first time we really started using that algorithm in a spatial way rather than in an ornamental way. And I guess that becomes this sort of point of intensity within the landscape, which is also generated through agent-based conditions. All right, so that gives a sort of overview of the type of formal concerns that have been evolving over the last decade or so in the work. The next bit is around robotics and fabrication approaches. So I guess a lot of the work I was just showing was really happening more than 10 years ago. And I guess we realized we were creating a type of architecture that really couldn't be built within current construction paradigms. And so we were left with a decision to make. Do we simplify what we're making, or simplify what we're designing to try and make it buildable within the current construction paradigm, or do we try and develop new ways of building so that we can realize the complexity of the forms and the articulation that we've been working on? And so, of course, we chose the latter. And at RMIT, I established a Robotics Lab, which has sort of evolved into part of the Tectonic Formation Lab. And when we first set up the Robotics Lab, we were looking at a whole series of different approaches, different tools. We're building customized tools for sort of taping and extruding, and using more conventional tools for milling or incremental sheet forming. And I guess we're sort of testing out what is possible. And of course, a lot of these things are quite known. We're also looking at slow robotics, this idea that robots can tend to biological growth. But a lot of the work that's really we've focused on for the last 6 or 7 years now has been around additive manufacturing. And initially, this was really around additive manufacturing of polymers and of plastics. So when we first began working with plastics, we began to realize that the extrusion of plastics works best if it's continuous. You can, of course, stop and start large-scale plastic extrusion, but it has certain technical problems that need to be overcome. And so we began by looking at what type of architecture could we make from continuous surfaces, and how could those continuous surfaces begin to fold and crease and corrugate as a way of making architectural expression and structure. What is the negotiation between the two of those things? So we went through a series of projects such as this one, where we're writing multi-agent algorithms. In this case, it's a mesh-based algorithm where each vertex of the mesh is an agent. And those agents are interacting with each other in order to create different types of corrugations or crumpling or folding or creasing based on its structural imperatives and formal aesthetic concerns. So in this particular pavilion project, you can see that in a section, there's sort of almost an arched-like element, which is a primary structural element, where there's a lot of creasing and folding to give significant structural depth, where the greatest loads are. But then as it extends towards the tips of the project, it begins to corrugate in the direction of the cantilever. And of course, by giving corrugations in that direction, it's creating structural stiffness in that way. So I guess this is a project in which it has a very strong performative structural logic, but that logic is tied up with a generative formation and concern with form and aesthetics and articulation of the project. And to us, these things are not things that can be separated. These are entirely interwoven concerns. So this was a competition and a project which then kicked off a whole series of investigations, I guess. And the first of those was at the Scentsy Lab Project, which was this one very small part of the project, which is this small meeting room. And it became I guess a milestone project for us because it's the first time we were able to 3D print translucent polymers in a real project which overcame fire codes and building codes and became a permanent piece of architecture. And I guess to our knowledge, it's the first time that this has been done. This project's now almost 5 years old. And so it was printed at RMIT. It was generated through this algorithmic logic where, once again, it's a mesh-based multi-agent system, which is generating corrugations at 2 scales. And so hopefully in this image, you can see this sort of a large-scale corrugation that's happening, and then a very fine-scale corrugation, which is then interwoven within that or overlaid onto that larger pattern. Of course, these are things which are generated through a simultaneous algorithmic process that's, again, polyscalar, something which is happening at multiple scales. The project was printed at RMIT in 10 relatively large pieces. They're printed from a transparent polycarbonate. Polycarbonate is a very, very difficult material to print, mainly because it has significant distortion during printing. So it's printed at a relatively high temperature. It's shrinking a lot as it's printing. And so there has to be a whole lot of mechanisms that have to be developed to overcome this shrinking and warping in order to enable it to be used within a project. One of those implications then becomes around how the project is detailed. So you can see as these panels are being installed, there is this sort of zigzag joint between panels. And this is a joint which enables the 2 panels to slide past each other to deal with the distortion that's happening within them. And I guess this was something which was new for us because we had this assumption that additive manufacturing is a highly precise technique. But actually, there's actually quite a lot of tolerance that's required in many additive manufacturing processes, particularly dealing with these higher temperature plastics. So as I said, it's fabricated in 10 panels. Here you can see that there's sort of 2 layers of corrugation. And one of our major concerns with the project and the corrugation was about the performance of light and the way light would reflect and refract through the material in order to make a space which almost glowed on the interior for this meeting space. In the background of that image on the right-hand side, you can see these sort of semi-expressed joints. Again, there on the left. Okay, that project was we were working on 4 or 5 years ago. More recently, we completed a project about 12 months ago. This is a project which is for an RMIT building. Again, it's a similar type of project in which there's an existing building. We've gutted the existing fit out and inserted a series of objects in the space. This is for a maker space and a design space. It's part of a larger collaboration with PMA and Zilka Studio, and in which we were trying to put teaching spaces within making spaces and look at their adjacency to fabrication spaces. And there's a pedagogical aim here to try and blur the relationship between design, making, and fabrication. So in the project, we're trying to create a series of transparencies or translucencies between these spaces. So we're trying to make views in and out of these design-based studios, which then look out into making spaces and create vistas through to heavier fabrication and workshop spaces. And so in doing so, there's different levels of transparency and translucency between those spaces. Sometimes you're looking through glazing to these translucent polycarbonate walls, or through a glazed window through a second glazed window. Tectonically, what we're trying to do is to make a more integrated relationship between the parts which are using additive manufacturing and more traditional fabrication. So this is quite different from what was happening in the Scentsy Lab project, where the additive manufacturing element was seen as a sort of unique element which attached to more traditional fabrication. Here we're trying to make some sort of transition between them. So on the right, you can see this acoustic wall has panel divisions, which are these metal elements. And that then transitions into the mullion system for the glazing, which transitions into a type of mullion, agent-based mullion, which is printed into the polycarbonate polymer panels. So you can see here, it's a metal seam which divides the acoustic material, which comes in sort of set sizes, so it needs to have some sort of jointing within it. You can begin to see how these metal seams then transition into the window framing. The same logic carries through into the mullions, and then the stiffening elements for those window assemblies. And that language then continues on, you can begin to see here, into a type of printed in mullion into the additive manufacturing part of the project, the 3D printed polymer. So in the previous project, in Scentsy Lab, this was quite a thick wall system. It used a triple layer, which almost became like a truss type system, which enabled it to have sufficient structural strength. In this project, we wanted to reduce the amount of printing. So we went with just a 2-layer system where the strength comes not from its structural depth, but from the geometry of these mullions that are printed within the panel. So these mullions then, the surface condition sort of shifts from the agent-based mullion system through to something which is, I guess, could be described as being more organic, again, trying to create certain reflection or refraction of light. So diagrammatically, you can see how that works. In these images, originally intention was to infuse carbon fiber structure within those. In the end, the geometry of the agent bodies became sufficiently strong to support the panels. And then there's a jointing system which is also built into that logic. So where you have this system of agent bodies, in a way it disguises the joint. You can see here at the center of the image, there's a mechanical fixing which attaches 2 panels. So this is a joint that runs vertically here. The one to the left of that is not a joint. It's just part of or the one over here is also not a joint. They're just part of the articulation of the agent bodies within the surface. So this became a slightly more sophisticated project where we're beginning to think about how do you relate structure and jointing systems into the continuity of these highly expressive panels. Again, you can see the joint here on the right, up towards the backlighting of these objects. And I guess this is an attempt trying to create something which is much more integrated. Now, we're very aware of the impacts, the environmental and sustainability impacts of using plastics. This is all printed from virgin material. What we're now trying to start to work towards is to try to work towards a way of 3D printing materials which have less environmental impacts. And so we've launched a research project which is around creating biodegradable 3D printed wall systems. So this is a type of sandwich-based wall system where we're 3D printing an inner and outer skin, and then in between we have a core material which acts as a compressive material, but also an insulation. So of course, we know what sandwich panels are. They're a very commonly used building type or building system. But what we're trying to do here is we're trying to print with biodegradable plastics and recycled plastics, and also to grow the core material. Instead of using petrochemical foam, we're interested in using a biological material, so in this case it's mycelium. So what we're doing is we're effectively printing a type of mold, which the mycelium grows in, a permanent mold. Mycelium, of course, is the rootstock of mushrooms, and once the mycelium grows within these sacrificial molds, sacrificial forms, they can be heated up. It's effectively killed off, and this then creates something which is a good insulation material and has a certain compressive strength. So what we're then interested in doing is looking at the way, and of course it's entirely biodegradable. This particular prototype here you can see is printed with recycled plastics. We're also, as I said, we're also looking at printing with bioplastics, so we can make a system which is entirely fully biodegradable. Now, because the core has a certain compressive strength, we then look at how we make a complete structural system by balancing that with a tensile system. So you can see here there's a series of veins on the skin of the project, and what these are for they're a series of conduits which enable us to embed composite fiber, which gives tensile strength. So if the inner core is compressive, then these veins give tensile strength to it. And what we've used in this project is use natural fibers. So we're using flax fibers, which are then composited using bioresins. So again, trying to create something which is not using petrochemicals and is inherently biodegradable. And I guess this marks a sort of shift or evolution in some of the work we're doing with embedding composites within 3D printed surfaces. So the previous project was looking at the way the fiber composite is embedded into an internal conduit. In this project, it's an external conduit which can be more easily accessed, and of course putting the strength at the exterior of the surface or exterior of the panel where most of the tensile forces operate. The last project I'll show today will show another version of this where we're embedding fiber composites within the skeleton. We have a relationship between skeleton and skin, a slightly blurred relationship between those two. Okay, so the last projects I want to show in terms of our work with explicitly with robotics is shifting from plastics into metals. So we've done a lot of work over the last 18 months with wire arc additive manufacturing, or WAM, and many of you, of course, Philip is very familiar with this technique. It's something that Joris Lahmann has done a lot of work on. It's effectively using a MIG welder on the end of a robot, which is laying down layer after layer of molten metal in much the same way that we're putting down layers of plastic in the previous projects. And so what we've been looking at is the way we can take some of our agent body logic, some of these fibrous lattices that we've been building at this incredibly small scale. Like in the first project I showed, those lattices in diameter, they were around 0.4 of a millimeter. Now these lattices are around a diameter of 30 to 40 millimeters. So we're sort of going up a scale of, almost a scale of 100. And this gives us a lot of, I guess, enthusiasm about the possibility of taking some of those thick fibrous masses we had in the early projects and the way we might start to realize these at a true architectural scale rather than the scale of an object. So these are some of the most recent work. These are projects we're actually printing this week, looking at the same type of agent body logic, but the way that might be printed in this case, we're printing in steel. Of course, WAM can be used to print many different materials, can be print stainless steel, bronze, aluminum, etc. We've also begun to look at the way we can make a hybrid fabrication approach, which is not purely trying to create the whole project through additive manufacturing. And this is a hybrid approach in which we're partially fabricating pieces of steel and then we're printing onto them. And so you can see here that it's a folded plate, which we're then printing steel onto, which are then joining together and becoming the joints of a facade, sort of small facade study that we're working on. And this allows us to use just here you can see brake press folded steel in a fairly sort of traditional manner. We can use large pieces of steel for the elements of the project which need to be blade-like or relatively flat or faceted. And then the more complex joints we're then printing those. And so I guess we're not trying to attempt to print the entire project, which is a relatively slow process, but instead figuring out which bits need that kind of complexity and which bits can be fabricated from a sort of simpler logic. And then trying to create some sort of relationship between the articulation of these plates. You can see these sort of dashed dot lines. These have all got to do with the way those elements are fixed back to the jigs. So there's a relationship here between how the thing is fabricated and what its articulation is. Okay, this brings me to the, I guess, the fourth part of the research or focus of my work, which is around tectonics. And I guess the point of departure of this is around these images. These were images we were creating, I guess, at the end of Kokuja, around a decade ago. And these were the images which were becoming, I guess, the most intricate and the most non-standard and the most unbelievable in many ways in terms of a construction paradigm. And it was around this stage where we were really starting to think about how we would go about using robots and using additive manufacturing or using different advanced manufacturing techniques in order to build these types of geometries. So our first instinct was to start to look at fiber composites, and we worked with a series of, we did this through academia a lot, and a series of workshops where we're looking at embedding carbon fiber and glass fiber networks of structure into surfaces, and looking at what is their structural performance as well as their expressive capacity. So this was the first prototype we developed in the lab, and this was really the project that kicked off what has now become the Tectonic Formation Lab. This was back in 2013, and it was really an attempt to try and compress surface structure and ornament into a single irreducible assemblage. And we talk about this as a type of compression of tectonics. So the project is generated through, I guess, what is now a similar algorithm to, or perhaps a familiar algorithm to this presentation, similar to what we began the presentation with in terms of a multi-agent system in which the agents are interacting self-organized to generate a type of coherent manifold topology. Each of the elements of the agent system are agent bodies, and they get compressed between layers of fiber composite. The way it was actually fabricated is there are three types of bodies, and they're cast in polyurethane foam, and they get laminated into a surface which is laminated onto a milled mold. So this is an example where we have to mill a mold for the entire project. This is that, so the jigsaw and the mold coming together, and the process is then layers of fiberglass fabric are inlaid into that mold. You can see in certain parts of this, you can see the relief in the mold for the location of those polyurethane foam bodies, which are then pressed into that, covered with more layers of glass fiber, and then vacuum infused. So this is a process that creates very, very thin fiber composites. So in the end, the surface is it's less than a millimeter thick. I think it's 0.85 of a mil thick. And the way it achieves its sufficient structure is partly through its form. So because it has a lot of double curvature in its form, through this manifold generative process, it's inherently relatively strong at its sort of overall surface level. But its real strength comes from the interaction between these very flexible or weak elements. So millimeter thick fiberglass is highly flexible. The polyurethane foam bodies that are inserted into this are also flexible. They're floppy. They're a very flexible foam. But when the two come together, they create something which is highly rigid. And the way they do that is that the foam material acts as a type of composite core. It gives a certain structural depth, relatively small. It's only about a centimeter, but that's more than 10 times the depth of the surface. So it enables it to have a structural depth, and then it also has corrugation, which gives it strength. So the idea here is that these agent bodies are connecting to each other to make continuous lines of structure, which are also expressive and ornamental, and they're creating that structure through, as I said, through structural depth and and corrugation. And in the end, what they're doing is they're creating something where you can't separate the ornamental expressive qualities from the structural necessity. These are one and the same. Now, of course, it's not 100% optimized structure. Like, obviously, there's a certain excess to these bodies, but at the same time, they're all performing a structural role. So that project's about 8 years old. Shortly after doing that project, we were commissioned to do something similar, but a much larger scale. The previous project was only 7 square meters. This next project is 70 square meters. And we realized that we couldn't use the same strategy. We couldn't use this almost digital craft-based strategy where we were milling an entire mold for it. Like, we knew we couldn't mill 70 square meters of mold. We also knew that we couldn't rely on our own craftsmanship in terms of inlaying these flexible bodies into this mold. We needed something which was more industrialized, something that could be given to an industry partner to develop. And so, so this project, I guess, is made of these sort of 3 large assemblies. Again, it's made from fiberglass, and it has this inlaid logic of agent bodies at 2 scales. So it's got this larger scale of agent body, which is milled from foam, and a smaller scale, which is extruded from silicon. And both of these respond to structural performance. So this is a bending moment diagram of those forms. And then what happens is the agents read the bending moment information and they respond to it. And they respond to it by orientating the agent body and their limbs in the direction of the bending moment. So what they're trying to do is resist bending. They're also sort of scaling their surface normal depth in order to create sufficient structural depth for the project. We also needed to use rigid foam, so it's much easier for in the end, the project was laminated by boat builders. So for the boat builders to be able to assemble the project, and this required us to do a lot of milling. So we were milling the front side of the foam, we were milling a jig, we were milling the back side of the foam. Some of it could be milled with 3-axis, some was using multi-axis robots. The smaller inlay was a much easier process. So this is something where we built a custom extruder to extrude silicon, and we're extruding silicon onto a very fine fabric. And then that silicon and foam is then inlaid into a mold or applied to a mold. The mold for the project is a reusable mold. So in the previous project, we made a mold for the entire project. What we're doing here is making one mold that's reused, make several different parts. It needed to be fabricated from something a little bit stronger, so it's MDF. And the mold itself is a composite. It's partly digital fabricated, partly built by these guys in the factory. So it's built by carpenters. And here you can see that this is those foam pieces being inlaid onto templates, and then it's being laminated into the fiberglass. And the idea is that then this one mold is used to make a series of pieces. Those pieces have a series of joints that connect them together, which you can see on the left here. The largest piece is designed to be the largest piece that we could fit into a semi-trailer and into a shipping container. And you can see here that then you end up having 2 sides to the surface. One side in the foreground, which is entirely smooth, which is the surface of the mold, and the other side, you can see on the left, which is this highly articulated side, which is different on every panel. So the idea is that there's a similarity of form across it, but an individual articulation of these agent bodies. So this was originally developed for an exhibition in Melbourne. It then traveled to the Shanghai Biennale in 2015. Now, that was a very time-consuming and difficult project to fabricate, mainly because it had a lot of milling and a lot of hand finishing. So we began to look after that project of ways of trying to fabricate these types of geometries in much simpler means, I guess. So this is an approach which we developed for a project in New Zealand, which is just simply using laser cut metal parts, which are then riveted together. And I guess we've taken the agent body network and we've written an algorithm which could then unroll and take apart this, this form in such a way where it could be reduced to flat pieces. And as each of the flat pieces connect together, they begin to generate and create their own double curvature. So it's a project in which you don't need formwork, of course. Now, we've then tried to develop how we can use this to make fiber composites. So in the same way that in the previous project, we had a metal, what we describe as a skeleton, which is made from flat laser cut pieces. This is then carbon fiber, which is being in sheet form, which is laser cut. And instead of being riveted together, this is now glued together. But as you glue the pieces together, they find their own form. They generate their own double curvature. So there's no mold required. And then we developed a technique for vacuum infusing a fiberglass skin over this, again without a mold, which then deals with all the shear forces and stiffens the skeleton, and of course provides a skin for it. So in many ways, this is a kind of important breakthrough in the way we'll think about composites, because in a lot of composites industries, like say the boat building industry, the mold ends up costing 10 or 20 times the cost of the individual part that's making from it, which of course makes a lot of sense. There's a lot of repetition, but the architecture that we're interested in doesn't have that repetition, or at least that repetition is often disguised within the project. And so we really need to develop ways in which we can avoid using things like repeated molds, I guess, which then leads to our interest in additive manufacturing, of course. So this was exhibited at the Talent Architecture Biennale about 6 years ago. Now, those projects, as the fiber composite projects were developing, they were shifting away from this original ambition for a thick fibrous mass, and they're becoming thinner and thinner. And I guess we got to the point where we realized we need a parallel line of research and experimentation, which is about lattices. And so this project, the Brass Swarm, is an attempt to make an agent body network where the agent body is, in this case, made from 4 brass rods. And the project really highlighted for us the importance of understanding the limitations of a fabrication technique and then building that limitation back into the generative algorithm. So the project really began by looking at the way we can use robots collaborating with each other in order to bend metal rods, and then understanding what the limitations of those were in terms of how far, what angle can we bend, how close could one bend be to another bend, what sort of sequence of bends can you do before the rods end up hitting the robots or hitting itself. And then we took all those constraints and all that logic and built it back into the generative algorithm, such that we knew that whatever the generative algorithm would create was inherently could be fabricated through this mechanism. One of the things we realized in doing the project was we were probably automating the wrong thing. We ended up automating the fabrication, and so the robots were able to produce the 270 rods required in one day. So it was bent very quickly. But then it took 5 people 5 days to assemble and weld this project together. And so in a way, we realized that perhaps fabrication is not really the problem here. Perhaps the problem is actually assembly. And it's something I'll come back to towards the end of the presentation with a recent project in terms of the way we dealt with AR and assembly. This is something we've also tried to scale up. This is actually a previous project we've done through the Digital Futures series of events, fabricated at Tonji University, where we're trying to go from these 900 millimeter long brass rods up to 1800 millimeter long aluminium rods to try and make a small pavilion. But our ambitions, of course, for this is to try and take it up to larger architectural scales. In this case, we're looking at the way it might be taken up to the scale of a pedestrian bridge. Now, both those two lines of inquiry have opposite problems. One is able to make a thick fibrous mass, but it has no surface. The other ends up getting compressed into thinner and thinner surfaces and doesn't have the fibrosity of those thick masses. So we realized that we needed to try and bring these two together, and to do so, we perhaps had to invert our logic in terms of fabrication, the way we think about the project. And it really came together in this project. This is from 2016. And this is a pavilion competition entry at the National Gallery of Victoria. And it brings together a lot of the streams of our research. So it brings together our interest in fibrous masses as well as mute volumes. So you can see the sort of interaction between the two of these. It also brings together our interest in articulated surfaces and lattices. So you can see in the project that on the surface of these more mute forms, they begin to delaminate into this more expressive network of surfaces below it, and surfaces and lattices, and it's sort of blurring between those two, blurring between where surface ends and lattice begins. But we realized in order to be able to make this, we needed to flip our logic. So instead of thinking about how do we build an agent body network and then produce a skin for it, we began to realize if we printed a skin or we produced a skin, we could then cast the structural agent body back into the skin. So we developed this logic that we describe as sacrificial formwork. And it was first developed on this project, so what is that now, 5 or 6 years ago, where we were printing these skins with conduits within them, and then we're coming back and casting high-strength concrete, fiber-reinforced concrete, into those skins as a way of making, I guess, highly complex and intricate structural networks and lattices. So you can see some of the prototypes here that we're working on. And I think this is something we're seeing now. In the last year or so, there's now been a lot of work in terms of 3D printing, using 3D printed plastics in order to make molds for concrete, whether those molds are sacrificial and permanent, like the ones that I'm showing today, or whether they're removable molds or dissolvable polymers. I think that this is a sort of, now a rapidly advancing area of additive manufacturing within architecture. We tested this on a series of projects. This is for a small public art project also in Melbourne. Which then brings me to a commission from the National Gallery of Victoria. This is a project called Flow, and I guess it's the first time where we really started to try and scale up this approach. But in doing so, we had very little time. We were commissioned to do this project over a 3-month period. So we had 3 months from when we started the project to when it had to be installed. And we were trying to build something which was 6 meters high, so it's the largest object we'd printed. And many of our strategies were about how do you de-risk the project. So the project was a collaboration with the sound artist Philip Simansis. So Philip takes these sound recordings from the Antarctic, and then this is Philip, and then he composes sound artwork from these. And what we were trying to do is we were trying to create a space which somehow captured the atmosphere of where these recordings were taken from. So we're trying to create this, I guess, ice-like or sort of Antarctic atmospheric qualities, and of course relying on the reflection and refraction of light through the polymer in order to be able to do that. So it's a highly atmospheric project. It's a project which had a very different quality of light from night to day. It was for a part of the triennial that was held here, and so the gallery was open till midnight. So it would be seen under various different lighting conditions during that period. And so it sits as this sort of very, I guess, sort of pure white object within this room, which has this very rich coloration. This is the Great Hall of the National Gallery. It has this amazing stained glass ceiling by the artist Leonard French. And then it has bluestone walls and the sort of deep burgundy colored carpet. Now the project is made from a swarm of 3D printed panels. And so there's 70 panels. All of these panels are printed at RMIT. They're all similar but different. So they all come from sort of a parametric family of panels, I guess you could say. You can see some of the differences in them here. So what's happening here is the panels all have a sort of parametric base, but the articulation, the sort of corrugation across them is something which is then continuous. It's not part of the parametric system. It's a bottom-up generative system. These are overlap, and they're printed with a series of different transparencies and translucencies. So some of them are sort of high gloss, some of them go into a more sort of frosted panel. And between these panels is a steel agent body structure that weaves between them. So it's not, even though the structure and the surface are separate, it's not a structure which is then clad. It's a structure which is interwoven between the overlaps of these panels. So this is an unrolled drawing of that, and the structural analysis that was done by Bollinger-Grumman. Bollinger-Grumman have done a lot of the structural work on this sequence of projects. And so that's then built in a relatively traditional way using laser cut steel and CNC brake press to fold those. The base of the project is built through more traditional 5-axis milled timber. It's made in a series of parts, which were then assembled on site. So this became a really interesting jigsaw puzzle of parts. We had 70 unique plastic panels. We had over 300 unique pieces of steel. And all of this had to be assembled in a 3-day installation period. So we realized we needed a way of assembling this that didn't rely on constantly going back to drawings. And this was just at the point where Hologram were developing their business. They were sort of, I guess, incubated as part of RMIT and then sort of launched as an independent company. And so we started working with Hologram to develop a way in which we could fabricate, we could assemble this without any drawings. So this is the NGB assembly team. That's more or less what they're seeing. They're seeing an overlay of the digital model, of course, and a short video from Hologram that is describing, how these guys went about working. So they were looking at the model, they were seeing the tag of what piece they needed, they were, getting that piece, putting it into place, and then, of course, all these parts are mechanically fixed. And this allowed us to assemble what's a fairly complex piece installation in a relatively short period of time. And if this plays, it's a video of the installation process. Okay. So the bottom pieces were individual bits of steel, and then every piece after that was a composite where the steel was attached to the plastic before it was being lifted into place and bolted into place. So you can sort of see in the end the project ends up being finished just before the opening, and that project was sort of attended by about 85,000 people over a 10-day period. Okay, so this was a way of very rapidly scaling the project up. And in trying to do it rapidly, we made a few concessions, I guess. We decided to use a steel frame rather than using a plastic structure. And this was partly a demand from Bollinger-Grumman. I mean, there simply wasn't enough time to prototype and test and engineer a fully plastic structure for the project. So we relied on something that's more conventional. But we also see this as something which is separating from our original logic of trying to embed surface structure and ornament into a continuous surface. So over a series of projects, we've then tried to bring this back, I guess, to embed the structure back into the surfaces, and also tie this back in with some of the painterly formation work we're doing. We were trying to look at blurring between forms and agent bodies, and sort of blurring between what is something that's purely algorithmic, where you can sort of read the logic of the agent body, through to something which is a continuous surface. And so what we see here, this is a sort of small Foyer installation that we're working on, which was testing that at a formal level. This is some of detailed development for a project that in the end wasn't constructed in Portugal, where we're looking at the way you can see so this white steel frame, which is now embedded within this continuous surface. So instead of being between these discrete panels, we're interested in the sort of the blurring of the agent body into a continuous surface. But we realized by doing this sort of study that actually inserting the steel in between the layers of the plastic is something which is, it's not a trivial problem. Working out how to joint the plastic such that you can print the plastic, insert the steel, and then close it up with other pieces of plastic means that there's quite a few sort of complex joints in the project. So we began to realize that it's actually easier to go back to our earlier logic where we're looking at casting material, or casting the agent body back into the 3D printed sacrificial formwork. But we wanted to shift from using high strength concrete into using fiber composites. And so again, this is beginning to blend our work with additive manufacturing and fiber composites. And this came about through collaboration with the aerospace company Boeing. And so we established a project several years ago in order to explore the relationship between 3D printing and fiber composites. And through that collaboration, Boeing has funded the several PhD positions, which are working towards so the technical details of how do you do this? How do you infuse carbon fiber into these printed assemblages? And so our first major test of this was a project completed about 18 months ago. This was for the Shenzhen Biennale. And this project, it's the last project I'm going to show today. And in many ways, this is really an attempt to try and bring together many facets of what we're working on. So it's trying to bring together additive manufacturing along with this sort of blurring between surface and lattice and thick fibrous mass, but then also being able to take it up to a more architectural scale. And of course, blurring the relationship, well, integrating between fiber composites and polymer additive manufacturing. So this is installation that's made from 13 parts. Those parts have the carbon fiber infused into them as individual separate discrete elements, which are then mechanically fixed on site. We're now working on a project which is sort of the next iteration of this, where we're doing away with the mechanical fixings and we're shifting entirely to a sort of chemical fixing. So everything gets glued together and is sort of glued, and the carbon fiber is laminated within it to make these sort of large discrete pieces, I suppose, as opposed to these mechanically fixed parts. There's 3 layers to the project. There's an outer skin, which is translucent, and then there are 2 inner layers, which are the layers of the agent bodies and down to the carbon fiber infusion. And what we're trying to do in terms of the sort of perception of this, or the affects of this, is try and create a sort of blurred relationship between skeleton and skin. So the idea that at some points the skeleton laminates to the skin and is highly visible. At other points it begins to recede deep within the volume of the skin, and it starts to have a more, I guess, more blurred relationship to it. Of course, like all our projects, it ends up becoming a relationship between things which we produce through highly roboticized and digital processes down to a lot of manual work as well. And so we're always interested in what is this relationship between sort of the algorithmic and the manual, or between the robotic and the sort of handcraft, and always looking for which skill or process or technique is appropriate to a particular part of the project. Like, this is not an ambition to try and automate all of architecture, or it's certainly not an ambition to automate the design of architecture. It's not an ambition to automate the fabrication of architecture. But what we're trying to do is trying to understand what are the very precise qualities and characteristics of a particular process, and what type of affect or articulation or structure that's able to create. And so I think I'll end on this project. And I guess the point I want to try and really make from this is to say that this transition in our work over what is now 18 years, from doing work that was originally purely algorithmic and purely about the digital, and then that started to interface with things which were then an interaction between top down and bottom up, and blurring that relationship. And then as those digital designs began to have to interface or interact with the constraints of building, whether they're fire codes and building codes, or whether they're the limitations of 3D printing, or what can or can't be printed or cast, I think these projects are beginning to become richer. And it's a richness that's coming through, I guess, the synthesis or hybridization of the digital processes, as well as the robotic and material agencies and material qualities. So I'll leave it there. Thank you. Neil,
Roland,
so
yeah,
I think we have,
maybe well, before Philip, until Philip comes and joins us, let me ask a question to get things going. Well, first of all, let me say thanks for a fantastic lecture. Wonderful. It's always good to see it. It was really inspirational as ever. Just and secondly, to the audience, please, if you have any questions, send them onto the chat. If you're on YouTube or Bilibili, please, we can relay them here. But let me ask you a quick question. It's actually very interesting because we had well, it would have been last night for Philip, but for us in the States, it was this morning. We had Akim on, and actually, what was interesting was that he was actually addressing very similar kind of issues, but a different way. I mean, this thing about in sustainability in terms of the material for 3D printing and so on. He even had an acoustic panel which he was talking about and so on. So there were lots of very interesting similarities going on. And I guess what was interesting though were the differences in a way. And we also had Hessam on for our PhD consortium earlier on, and he was showing some of that work. And one of the questions that came up was, I mean, it's one that I asked really in some ways, is it's in a sense, there's a kind of spectrum, right? At one end, you've got Akim, who's not completely at the end, but he's very much into kind of performance-based logic itself. And then you're not at the other end either, but you're kind of more towards the other end, as it were, in terms of kind of what it looks like. And then maybe one could think about other people who are not interested at all in performance, and they're kind of even further over. But there's this spectrum, and it's kind of like it's an interesting issue about how do you balance it out, because I guess that what I always find interesting, and that's what I said to Hessam, was really with MIT Media Lab, for example, it's kind of interesting because they have this kind of conflict. Are they designing something, or are they doing something that's this kind of scientific research? And in fact, in terms of MIT, I understand that they're looked down upon because they don't bring the funding in enough. At the same time, we in the design world look up to them because they're so rigorous and so on. So it's that challenge about how do you find the balance? But more importantly, I think to my mind, it's how do you kind of quantify, or how do you judge what you're doing? Because I think Akim's work is easy enough; it performs, and that's it, and it happens to look nice. But yours is really, it looks great. So how do you elaborate some kind of framework for judging it, or should you even do that? It's just a kind of like, to my mind, there's a real challenge there, and how do you deal with it, with work that is exquisitely beautiful and has some performative capacity, but but it's not clearly the most important capacity.
yeah, okay. There's a lot in there to unpack, but it's super interesting set of questions. Look, primarily I see architecture as a cultural pursuit. Like it's not a technical pursuit, it's not a scientific pursuit, but it's something which is cultural. And so if you think about what is the performance, or what is the criteria for cultural production, it's not something that can be quantified in terms of weight or structural performance or some of these other criteria, which perhaps some other architects, as you say, at another end of the spectrum are concerned with. However, in order to be able to build these projects, in order to be able to make them feasible, in order to be able to make them sustainable, they have to engage with those things. And so I guess what I would always say is that my work is driven by a set of design concerns, but it's heavily conditioned by a set of more pragmatic and technical concerns. And I guess to put it really crudely, I would always say that building science is simply not interesting enough to be a driver for architecture. Like building science is something which architecture simply must respond to. And I guess I describe it as being conditioned by or negotiated with. So yeah, certainly my projects are never led by something like structure, but some of them are quite structurally optimal or structurally innovative, I'd say. But then the second part of your question was really about how do you, what is the criteria for the work then if it's not something which can be quantified? And I think this whole question has large implications around AI, machine learning, and automation of design as well. Because if your concern is something which can be quantified, then you can work out automated ways of designing that. And Neil, you and I have of course talked about this in terms of 10 years ago we were talking about this in terms of genetic algorithms and our discussions with John Holland. And of course this is something which also comes up with machine learning techniques such as reinforcement learning, where you have an a priori criteria which you're trying to work towards. You, of course, have to be able to write that criteria, and that criteria has to then be numerically describable. Now, if you're interested in things which aren't numerically describable, which is what I'm interested in, I guess it suddenly becomes a lot blurry on how do you describe these things. And for me, it's been most interesting actually working with students. Like the one slide I showed of student work with the sort of the colorful objects, that comes from a whole series of studios that I teach at RMIT. And a lot of the discussion in those studios is about incredibly subjective decisions about form and aesthetics. But they're subjective, but they're in no way arbitrary. And what happens is a language of, like, if you look at those sets of objects, there's a sort of a certain consistency to them and a certain coherence of language. And so it's never arbitrary, and it's not like, the idea that subjectively one object is equivalent to another object. But there's a series of, I guess, concerns or criteria that begin to emerge through the act of doing the work. So they're not a priori things. They're not things we sort of say, okay, we know what where aesthetic value lies or where formal value lies. But by doing the projects, we begin to find traits that we value. And those might be things like part to whole relationships. It might be about the sort of the blurring of the continuous and the discrete, like what is the interface between those. It might be about sort of self-similarity or transition across scales. It might be about we often use this term haesty. And haesty is, I guess, can be described crudely as the thingness of a thing. And we're interested in the thingness of objects and the idea that an object has haesty or has becomes a thing when it's sufficiently internally coherent. And so I guess what we're searching for in our formal and aesthetic explorations are formal aesthetic languages which are internally coherent and become a sort of thing in themselves, as opposed to a series of sort of arbitrary judgments. So I mean, it's quite hard to describe really without talking about the particular objects, but maybe that gives some sort of overview.
Maybe I can just briefly follow up that with a particular question about the Boeing collaboration, because I thought that was kind of interesting. Because what in the context of that, you were collaborating with Cecil Baumann, who was an engineer who really appreciated what you brought to his world. I'm just wondering if the Boeing guys who are asking you to sort of explore this particular technique, whether they appreciate how exquisitely beautiful your work is, whether that's an issue. I don't know.
We spent a lot of time collaborating, and so the way that collaboration came about was Boeing saw the work we were doing with Fibre Composites and those very thin fibre composites had no formwork, and they were interested in that, for obvious reasons. And they're also interested in the additive manufacturing work we're doing, and so I guess what I was able to do is convince them that what we need to do is bring those things together. And we set up a research project which was devoted to integrating carbon fiber and 3D printing across a series of projects which were not a building, not an aeroplane, but somehow something in between those two. I mean, that's a very crude way of describing it, but we're trying to make these things which are tectonic demonstrators, where there might be some sort of technological or sort of technique advancements or IP that could relate to aircraft design. It might relate to building fabrication. But these were sort of abstract things in themselves. And so as part of that, we then put out a call to try and employ several PhD candidates as researchers on the project. And then those guys then started working through, I guess, the nuts and bolts of how do you do that? Like, how do you infuse carbon fiber within these systems? I mean, should it be continuous tow or does it need to be braided carbon fiber? And, looking at what those sort of high technical things are. But in terms of when I talk to these people, I mean, Cecil Baumann is quite unique as an engineer because, his work is very rooted in design, and it almost has a mystical quality, to be honest, the work of Cecil. But a lot of the other engineers that we work with, say at Boeing, these guys, they deal with some very pragmatic, dry problems every day. Like the guys we work with at Boeing are like looking at like how do you shift from prototyping to fabrication on like, you know, autonomous drones or something. And it's like there's very, very, very technical questions. And for us, for working with us, it becomes this opportunity for them to sort of think in a very blue sky way and say, okay, how can we kind of completely think outside of that? And the advantage we've got on the Boeing project is there's no real set deliverable. We're not trying to achieve something in particular. We're simply trying to experiment. And they've been incredibly generous in that way of saying, we're going to support entirely experimental work with no intention for where it's going to lead. But with this idea that, you know, something might come out of this, which has broader application.
Great.
Thank you.
Neil, shall I have some feedback?
Yeah, go ahead. Yeah.
So, Roland, thanks a lot for the great lecture. I'm jumping back and forth because I'm teaching in the studio. So but I see how the process of your introducing is fantastic. You make a huge progress compared to last time, maybe 2 years ago, you make a presentation to us. So I think it's really important to have Roland in our community because Roland's contribution is very special. I think I want to express my feeling of Roland. I think at the same time, on the one hand, Roland is a talent designer. He is a formalist, as Neil mentioned, and I think formalist here is a kind of pioneer and avant-garde and leading the big army going to a different direction. But I think we need some figure like Roland. He insists in his own feeling in architecture, which is based on bottom-up process and to make special potential possibility to generate form, to make the industry rethinking on the design and the making process. I think that's extremely important. But at the same time, I think Roland is very good at sharing his knowledge to the others. So everything he's doing, actually teaching different people, and also the scripts, everything is open source from Roland's research. But in the meantime, it's especially difficult to follow what's Roland doing. So he has his autonomous speciality for his style. So that is a very interesting thing because although Roland have a lot of students, but seldom of his students can learning the style from him. So that's a very special, unique phenomenon, I think. I met a lot of his his students, but all goes to different their own career, their own creative process. But they're learning something else from Roland, not just the formalism, the form, how to generate form, but learning some spirit. I think that is something to explore the potential possibility. It's a kind of experimental skills to engage their whole life into certain things they love. So I think that is something I can learn from Roland. It's 10 years, we know each other around 10 years, but I think the 10 years have some similarity, but at the same time it's quite different. We can see the multi-material integrate agent-based formation process, and also right now introduce different kind of robotic technology, robotic crafts into the fabrication of your form. So I think it's we're sharing some similar methodology in robotics. I think we're also doing some plastic printing and steel welding, but I think the form is totally different. You have your own specialty in the agent-based formation methodology. So that's the very special part. So the question goes to Roland because your specialty makes you Roland unique. But at the same time, I think this time we introduce you to the China Construction Group to teach a workshop in digital futures this year. And so I try to curious want to see what's happening when you collaborate with industry, because China Construction Group is the largest construction group in the world, and they actually invest a lot in the facilities in the robotics right now. And maybe in the future they will have hundreds of robotics in their in their factories, but they also curious on what they're doing. So I want to hear some voice from your side. What do you think? How would you like to introduce your own research to the industry, not only in Australia, but also it's a global infrastructure system for the future robotic industry. So how would you like to address your research, your practice into this global culture?
Philip, thanks for the question and the very generous comments. Look, it's a real challenge. I mean, when we started doing this shift from computational work into fabrication work, we were trying to develop fabrication approaches, and some of those things were scaling up existing processes. So, for example, when we started trying to print with plastics, we were scaling up, of course, what happens on a small FDM printer. And at the time we were doing that, that wasn't something that was being done in industry, and we didn't have. We knew the things that we were designing and we were prototyping in the lab. We couldn't simply go out and have somebody else build for us. So our initial instinct with that was, how do we take our technologies and transfer them to industry? And we've done that with, so one of our projects, the Building 515 project for RMIT, that project was the only project I showed that wasn't fabricated by us. So we actually basically helped to set up a robotics cell in a fabricator in Queensland, in Australia, and they then printed the project. And so that's an example where we've sort of refined the technology, like large-scale 3D printing. We've transferred it to a industry partner, and they've been able to then print our projects. But I think this is changing so quickly now. It's changing so quickly that when we did that project, when we started that project 2.5 years ago, there weren't anyone who could print it for us, so we had to help a company to be able to do that. But now we're in a situation that's very different, where there are, we can tender that project out now. There's a series of companies that would be able to bid on that project and would be able to actually 3D print that project. So I guess it's changing from a logic of having to invent something and transfer it to industry. And we've seen this with like Ramatio Cola, for example, with their sort of their robotic bricklaying. They developed that technique and then they transferred it to industry. But your introduction to the this very large construction company in China, this was also a really interesting thing for us, because we didn't need to transfer any technology to them. They simply said, yes, we can print the formwork for it. We can cast the ultra high strength concrete into it. We can print the WAM, the wire arc metal for you. And so I guess what it makes you realize is that the lifespan of the invention of technique or refinement of a technique and transferring to industry, it goes very quickly from a point of like, this is entirely bespoke and it happens in labs, and it's only available to the very few who actually invent these things or develop them, to suddenly being something like, okay, the largest construction company in the world now 3D prints molds for concrete. And so it's those kind of changes will have radical effects, because all of a sudden it means that those technologies are open, democratized, they're open to everybody. But I think what will be really interesting then is to see how architects deal with it, because the architecture that I do has evolved through the constraints of these tools. We're so intimately aware of like what we can and can't print, that everything we design is based around that. And we're things like the project in Shenzhen, that was just trying to push the absolute limit of what could and couldn't be printed, in terms of complexity of geometry and topology. I think architects who haven't gone through this process of doing their own prototyping and building their own things are going to have a very different kind of interaction with the limitations. And it'll be interesting to see whether it's something where architects bring, I guess, a more traditional logic of architectural design and just try to fabricate those things. And then, of course, some of them they can fabricate, some of them they won't be able to fabricate, or whether there'll be a sort of rethinking of this, of the way you design through these techniques. And I think this is very normal. Like we see this with like concrete printed houses. There's a whole lot of concrete printed houses, and none of them take advantage of what you can do with concrete printing. they always use concrete printing as like, you know, just a replacement for an older technology. And I very often, when I'm talking about this, I show a slide of an image of the first iron bridge in the UK in the 1770s. And the first iron bridge was built with timber jointing details. Like, it looks like a timber bridge. It's just replaced timber with iron. But it took a long time for bridge design to evolve into you know, contemporary bridge design that uses tension and compression structures in very different ways. And this is the same with aircraft. Like, it was fascinating having this relationship with Boeing and realizing that they talk about carbon fiber as being black aluminium. And what they mean by that is that because aircraft design is such a risky business, obviously, every advancement in aircraft design is very incremental and very small. So when they started building carbon fiber aircraft, they didn't radically reinvent the airplane. They just replaced aluminium with carbon fiber, which became stronger, you know, lighter weight. It's a better material, but there's still, most of the carbon fiber in aircraft, there's still a lot of, like, you know, a lot of ribs that are cut from flat sheets and all these things which are which don't make sense in terms of if you sat down to design a plastic aircraft. It would be fundamentally different from a metal aircraft. But this is what we also do in architecture. You know, we just replace one technique with a new technique, or one material with new material. It takes a long time for us to actually evolve how we, you know, we rethink architecture through those. And I think, you know, that's why I like to think the work that, you know, somebody like yourself, Philip, you're doing in terms of, like, you have the fabrication means, you're intimately aware of what, you know, the robots are capable of, or, you know, what happens at ICD or ETH or happens at our lab at RMIT. I think that this allows you to accelerate that sort of reinvention of architecture through the means of production.
Great.
Daniel Bollinger has a question.
Daniel.
Hi, Roland. Thank you very much. It was an amazing lecture. So I think my question, or yeah, maybe I want to move a bit the discussion towards the early part of your presentation, and mostly because I think I'm mostly interested in this idea of design agency of design more than parts of fabrication, let's say. And I think your work, it's really a great example of this kind of idea of how you go beyond, in a way, certain tools and this kind of problem that you're talking about, tool indexing. In a way, it's very often it's very obvious, in a way, the tool that someone uses. And I think in your case, it's really great to show, like, how design intention can be encoded at a very granular level, in a way, and then allow those behaviors that you're designing, in a way, to self-organize in a sort of process of self-organization. So for me, in a way, the question will be, or what I'm trying to ask a question is mostly in the side of AI. Probably right now, probably you're engaging with some machine learning algorithms, but I'm very curious, in a way, because also in your work, again, you have this kind of a topic of agency and the problem with parametric design, and why this kind of generative, or not generative, but morphogenetic, in a way, systems like swarm systems actually allow for more granular level of encoding than parametric models. I'm curious, in a way, how you see, in a way, this aspect of AI, because right now I mean, there is a very, very strong, in a way, not preference, but trend. Let's say people start to use a lot of AI these days in design. And it's, again, this kind of problem of how you're addressing the tool, the role of the designer in the process. Are we talking about a very general tool that just designs everything, or we are talking about processes, like similar with swarm systems? Yeah, so you can take a swarm system and then you just, if you don't go to a deep enough level, you end up with a very generic, in a way, solution that everyone has. Yeah, and the same happens also these days with AI. For example, the outputs that we get from AI, they are very generic in the sense of it's very easy to see the tool that you are using, actually. Yeah. So I'm curious, in a way, what's your take on that technology, and a few maybe insights that you can offer when it comes to how you take this kind of tool and then how you should start to think about aspects of design, encoding agency, encoding design intentions, and so on.
Look, it's a really interesting question. about 3 or 4 years ago, we started a collaboration with computer science department, and in fact the computer gaming department at RMIT University, who are experts in machine learning, in particular in reinforcement learning. And my interest in AI is largely around, and its interrelationship with multi-agent systems is around this sort of radically different way of thinking about design. So, I mean, of course, you understand the systems very well, but obviously the bottom-up systems of multi-agent systems are about encoding bottom-level intention and allowing something to emerge from that. AI, of course, works at the surface level, and then the decisions you can make within AI are about the artifact, not about the underlying process for it. And I guess I've realized throughout this now sort of 18 or 19 years of working with multi-agent systems that some problems can't be addressed from a bottom-up local level. And I talk about this in terms of global ignorance, and this idea that a multi-agent system is ignorant to what happens at a global scale, and it's actually, that's important for it because that's what allows it, of course, to have a generative self-organizing capacity. But some things such as enclosure or structure or a whole series of architectural problems can't be understood from local interactions. They must be understood at a higher level. So we've got around this through these sort of strange feedback systems where we interact with the multi-agent system by doing some modeling, some multi-agent work, and then that allows us to sort of compensate for the limitations of multi-agent systems. So my interest in AI is another form of compensation for it, because if AI works at the global level, the surface level, then if you have these two ways of encoding intention or think about intention, one is like you look at your intention within an AI system that deals with the global problem. The multi-agent system, of course, deals with the bottom-up self-organizing problem, and the way these two interact could be fascinating. Now, of course, it turns out, and you may well know this, that there's a huge problem between the logic of machine learning in terms of reinforcement learning and the way it works with a sort of singular machine as opposed to multiple machines. And so actually the logic of reinforcement learning and the logic of multi-agent systems are so diametrically opposed that they actually don't play very well together. So we've had a PhD candidate, Dasong Wang, who's in his final year of his PhD now at in my lab, and he's basically been working on this problem for a number of years now. Like how do you interrelate the two? And he's kind of worked through a series of strategies in which he has made a sort of quite meaningful relationship between the two, and he is able to use reinforcement learning to train what it is that the agents are doing and get them to respond to a high level problem. So that seems like it's quite productive. But of course, the reinforcement learning, the way it works on a reward structure is not at all dissimilar to the way a genetic algorithm works on a fitness criterion. And this is something that Neil and I have talked a lot about. In fact, we had a fascinating conversation with John Holland about it, the late John Holland, about 10 years ago, where we talked about the problem of the fact that with a genetic algorithm, and same with the reinforcement learning within machine learning, if you're writing the fitness criteria or you're writing the reward structure for it, you're already a priori deciding what is a measure of success. You're already sort of describing what it is that you're trying to create. And this comes back to this whole problem of like, is it speculation, or is it true experimentation, or is it something which is working within a known realm? And I guess my concern about AI is the fact that it's always bound by its own a priori realm. And this is something that, I think you've probably heard me talk about in terms of parametric design. I've always been critical of the fact that parametric design is always constrained to its initial conditions, its initial setup. AI is very similar. I mean, because whether you're working on supervised or unsupervised learning where you have a data set, it could only operate within the bounds of the data set. If you're using something like reinforcement learning, where you're writing, it doesn't have a data set, of course. So in that way, my assumption, of course, was, okay, this is going to be more generative. This is going to have the capacity to be more speculative and more experimental. But of course, you're writing what is the criteria for it. So I guess that's why I'm really interested in the relationship between the two, because it's the bottom-up generative self-organizing capacity of multi-agent systems and their capacity to generate emergence, I still think it's sort of fundamental. Even though we've been working on this for 2 decades, I think it's fundamentally interesting and important aspect of design. And if you say, well, maybe the ambition for AI is not, as a master designer, it's not like, using AI as something which is like the entire design system, but saying, okay, AI is something which can augment other forms of generative design. It can bring a sophistication to other forms of generative design that they previously didn't have. I suspect it's something about the hybridization of these techniques that to me, I think is the key. But this is also my bias. I mean, you've heard me today talk for hours about the fact that everything I do is about some sort of hybridization, whether it's like surface and lattice or, the bottom up or the top down. I'm kind of like obsessed with the blurry zone between things, I suppose. I don't know. So it's very, very long answer to your question. I'm sure you've got a follow-up.
Yeah, can I just follow up a bit? So yeah, I think I agree in a way with you here, because in AI, mostly you're going to talk about 2 main types of creativity, or not to go down on that route now, but you talk about interpolative and extrapolative in a way creativity, meaning that the first one is mostly constrained to its data set, and the other one actually tries to generate something outside of that data set. And I think, I mean, you're right, and I think I have similar processes when it comes to working with AI, having this kind of thinking, almost like using the analogy of the swarm. You end up actually with networks, almost like agents, and then it's the interaction between these networks that actually gives you the design, not necessarily this kind of like you're describing it, like this kind of general designer that just designs everything. Yeah, it's mostly about which is the design process, where do I have to encode what kind of intentions, which are the levels of designs where I want to encode, and what kind of system networks I have to use for that. Yeah, and then it's a sort of interaction between these networks, that generates something that we call design, let's say. Yeah. So I think for me, in a way, that's what where I'm drawing my inspiration from, mostly from agent-based systems, because before I jumped into AI, actually, I was very involved into agent-based systems as well. And I think there are a lot of good lessons in that realm, in a way. And I think it's also something that we have to be careful not to just throw out the window. Yeah, because right now I think there's a tendency when working with AI just to make this kind of very broad statement where we are saying, well, AI is just going to learn how to design and that's it, yeah. And we are going to ignore everything that we learn when it comes to generative systems, when it comes to morphogenetic systems and so on, yeah. And we're just going to assume that somehow AI is just going to learn everything. When I think it's mostly about, like you're also describing it, it's about procedures, methods, different methods that you're playing with, and allow them to interact.
Yeah, I think the key thing here is it's conceptually different way of designing, and I guess I see value in both, but I still think I have this sort of bias towards the capacity of self-organization, because I think it's able to create things which are unique in a way that designing through surface effects, it's much harder to do. So, but yeah, so I guess I see it as an augmenting technology.
Theodoros, do you want to ask you a question?
Sure, yeah. Thanks. First of all, thank you, Roland. It was a brilliant presentation. Amazing work, I think, that you've shown through the years. I will resist my temptation to sort of go into the discussion that was just going there. I have a lot of thoughts, but for another meeting. I want to ask something more practical, again, also at the early stages of your presentation. So you talked, and just now you were discussing about agent-based systems, behavioral, focusing on the behavioral dimensions of design, right? So lately, one of my biggest criticisms for parametric design is that, also when I was doing it, all we do is work on the design, on the input space, right? So we have a sort of sliders or whatever you have and you move them around and you create new designs in a way. But in fact, what we should be caring about is what is the behavioral space of our design. So like, how does the design sort of behaves, or where it positions itself in a space of, for me, performance, for others, aesthetics or structure different. So my question is, through the years, have you found any specific maybe behavioral dimensions, or maybe heuristics to identify those that are important for design evolution or exploration? Like anything that stood out that, you know, this sort of technique or this sort of was important and gave us diversity or new designs or something like that?
Okay. I'm not sure I fully understand the question, but in terms of there are a whole lot of heuristics that we will build into agent-based systems, which respond to, you know, things that we can think about heuristically, like for example, structure. So we've done a lot of work with agent-based structural systems where we have an agent-based network which is you know, constantly reforming, and as it's doing that, it's running FEA analysis, it's checking its structural capacity, which of course FEA analysis is a global level thing. You know, structure it's a global condition, but it's relaying information back down to the individual agent at a local level. So this is a kind of interesting relationship between the top down and bottom up. But then what the agent is doing is it's operating on heuristic principles. So it's saying, okay, there's too much deflection here, so therefore we need to increase vertical separation between the agents in order to create greater structural depth. So that's a, you know, that's a very, very logical structural heuristic that, you know, we can, you know, agree on or something, and then encode those into agents. So they're sort of taking, you know, in some ways you can describe it as sort of real world information, like it's sort of FEA, and then they're responding to it through, I guess, it's kind of logics that, you know, that we invent, you know, heuristic rules of thumb logic. I don't know, is that what you're asking, or
I think yes, or maybe if I can rephrase it, would you think, or did you find through your work that something like that, linking it to a heuristic that may be performance or not, does it create something more interesting than just a bottom-up approach that doesn't link it to anything? Is there a possibility that we could do the same, you know, we could do as well at that front by also linking it to some global information?
Yeah, okay. Yeah, look, absolutely. I think that it's the interference with the system. It's the constant interaction with it. It's the negotiation between you know, the bottom up and top down, which is totally the key to this. And you know, it goes back to what Philip was just talking about. And you know, I guess here I'm described as a formalist. I wouldn't necessarily describe myself as a formalist, but I don't mind that. I think I'm quite happy if people describe me that way. But the thing is that I want to try and put in as much design intention into these projects as possible at every possible level. And so I'm very happy to put intention in terms of starting conditions, in terms of like bottom-up behaviors, in terms of the criteria for an AI, in terms of the way you then feed things back and make decisions around things at a top level. Like, I think as many design decisions you can make about a project, the richer the project's going to become. And actually, you know, perhaps I'm more esoteric, and I say esoteric in a kind of very positive way. I mean, I'm through my work, I'm trying to find something that's unique. I'm trying to search for like a kind of language which is individual, I guess. And I guess that's why I describe architecture as being inherently as part of the humanities. It's a creative, it's a cultural act. And I think that if you're entirely reliant on the systemic, you can never do that, right? And so that's why I sort of always resist the purely systemic. But at the same time, I'm probably, you know, more engaged with, you know, these systems than almost anyone in design. So, you know, it's sort of like I'm obsessed with the systems. I have no choice but to use them. But at the same time, I'm always like, you know, in a constant battle with them to try and stop them kind of drifting towards the generic.
Thank you.
We got a question from Mohammed Bejo, who's in Iran. Theodoros, I should say, is in Kuala Lumpur. Daniel's in on the East Coast in Fort Lauderdale. I'm in LA. So we're spanning the globe today. Mohammed, are you able to speak? Can you unmute?
No.
We can't see you. Could we be able to see you as well?
No, just we might.
You don't have a mic. Okay. So let me ask you a question. Yeah, I'll ask you a question. So his question is, it's actually in the chat, but is it possible in the near future to print materials or organs that are alive, like mycelium or some materials that respond to environmental stimuli? Or even let's think of a building as a body. So can we have a 3D printed space that will grow? So maybe the first application of it that comes to mind is that the building is able to grow and get bigger or smaller in the coming years. In some scientific fields of 3D printing, their final goal is to 3D print a human. So is it possible to think of a living and growing city?
Well, excellent question. Yeah, I mean, we are printing. So the project I showed around mycelium is obviously growing mycelium within a 3D print. But that work's been undertaken by one of our PhD candidates, Natalie Lima, and her another side of her research is around 3D printing of mycelium, basically. So it's a sort of a paste which contains mycelium and nutrients, etc. And she's printing those things, and the mycelium then kind of continues to grow and overtake those structures. And so the idea that you can make a living architecture, I think that this is something that this is not so much my ambition. My concern around mycelium is around its biodegradability. It's sort of a environmental or sort of climate concern. But yes, there are people who are working on that, and that somebody like Natalie could talk about that. She sort of talks about architecture for mycelium rather than simply mycelium for architecture. With the mycelium example, of course, the thing about mycelium is actually it's stronger when it's dead, and so you actually have to heat it up, kill it off before it becomes sufficiently structurally stable to be used as within buildings. So I guess there's a sort of bit of a problem there. Like, living architecture is best off dead. With that very negative note, Neil, I'm out of time. I have to move on to a PhD confirmation session.
Roland, thank you so much. It's been great. And, I just said to Akin this morning or last night, whatever it was, it's amazing now we've been able to use this platform to get this message across. And I think, the comments coming in from the chat, I mean, you've got a big fan club out there. I should say Daniel also has got a fan club. They loved his question. So I think it's really kind of been fantastic. It's validated our idea that we could span the globe and bring everyone together in this intense thing. So, it's allowed us to share ideas in a wonderful way. Thank you, Roland. Thank you so much. I just want to say one thing is I look forward to catching up in Shanghai for a Moscow Mule sometime in the not too distant future, because it's fine to be online. It's even better to be in the Constellation Bar and have a good chat.
It's too long between drinks, Neil.
It is.
Neil and Philip, thank you very much for having me. It's really great to be. I really enjoyed the conversation. Really great to be part of these things. And yes, likewise. I hope to catch up sometime soon.
Thank you, Roland. Thank you so much.
Thank you.
Thank you.